Welcome to Chapter 5 on double integrals. In this video, we're going to start section 5.1 on the definition and interpretation of the double integral. The goal of this section is to use the definition and interpretations of the integral of a function of a single variable to develop corresponding definition and interpretations of the double integral of a function of two variables. So let's do section 5.1.1, reviewing the single integral. So if we remember from integral calculus, the definite integral of a function f of x on an interval ab was given as the integral from a to b of f of x dx is the limit as n goes to infinity of the sum from I equals 1 to n of f of xi star times delta x. And I'll remind you in the figure below what these symbols mean. But this part here, the argument of the limit, was called a Riemann sum. So the most common interpretation of the integral is a geometric one. The integral represents the area, actually it's the net signed area, under the graph of f of x from x equals a to x equals b. So let's sketch this interpretation and remind ourselves of what some of these symbols represented. So if this is our graph of f of x, and we're looking at the graph from x equals a to x equals b, then you probably developed the definition by trying to get a handle on the area of this region. So you divided the region into n different subintervals, or you divided the interval a to b, and each of those subintervals you called delta x, and that was b minus a over n. Now you wanted to get area, so you wanted to turn these shapes into rectangles. So you wanted to draw a height somewhere across, but there was a question, where do you draw the height? Do you draw it here? Do you draw it there? Do you draw it somewhere in between? Where do you draw the height? And so the solution was you picked a point in each subinterval called a sample point. So x1 star might have been here, x2 star might have been here, x3 right in the middle. You may have chosen all right points, or you might have chosen all left points, or you might have chosen random points. And what you did with those points was you evaluated the function at those points. So that point there is f of x1 star, and similarly f of x2 star and f of x3 star, and so on and so forth. And these function values, that's where you decided to draw the height of your rectangle. So each of those rectangles has a base, that's delta x, and a height, that's the function value at some sample point. So you took this information and you said, well, the area of one rectangle, well, that's base times height. So that's the height is f of xi star, and the base is delta x. And then you said, well, the area of n rectangles, and that is actually the Riemann sum that you called Rn. That is the sum from I equals 1 to n of f of xi star times delta x, and then the exact area is when you let n go to infinity. So the number of rectangles, the limit as n goes to infinity of Rn. And that is actually where the definition of the definite integral came from. So fundamental to this interpretation is the assumption here that on small subintervals, f of x may be taken as, well, what's a flat line? Approximately constant. And the value of this constant is found by evaluating f of x at what is called a sample point. within each subinterval, and that sample point is your xi star. In the interpretation of this integral as area, the constant value is f of xi star, and it represents the height of the rectangle on the interval. But that isn't the only interpretation. The interpretation as area is the most common, but there are others. Let's go and take a look at a couple of them now. Other interpretations of the single integral. For example, if f of x is rho, that's the Greek letter rho, rho of x, if it represents the density of a thin rod at some position x, for example, in grams per centimeter, then the integral represents something interesting. It's the mass. Let's take a look. So if we imagine that we have a thin rod, let's say we have a rod on the x-axis, so I'll draw it with a little bit of bulk to it so that we can have a good drawing. So that's on the x-axis. There's a y-axis here, and that goes from A to B. And let's say that we're interested in the mass of this rod. This is what we want to find out. Well, all we have is the density, rho. The density is given in grams per centimeter. So we need to multiply the density times the length to get the mass. The idea, right, if you remember about canceling units, grams per centimeter times centimeters, those units cancel, and you get grams. So we need to multiply the density by the length. But the problem is that that density is changing. So how do we deal with that? Well, we're going to make the same kind of assumptions as with area. We're going to divide the rod into n subsections. And so the length of each subsection is going to be delta x, and it's going to be b minus a over n. And then we're going to assume, and this is the fundamental assumption, we're going to assume that the density is constant. So instead of height being constant, we're going to assume the density is constant on each subsection. Perfect. If the density is constant, then we can multiply it by the length. But wait, how do we get the density value? The density has to be evaluated, so we're going to pick some sample points, x1 star, x2 star, etc., and we're going to assume that the density, so rho or f of xi star, is the constant density. So instead of constant height, constant density, but evaluated exactly the same way by plugging a sample point into the function. And so then the mass of one subsection, well, that's going to be the density times the length. Well, the density is the density function rho of xi star times the length. Well, the length is delta x. That's the mass of one subsection. Well, of course, if we want the whole rod, we're going to add up all the subsections. So the mass of n subsections is the sum from I equals 1 to n of rho of xi star times delta x. Right? So that's the mass of n subsections. Now I want the exact mass, and so I'm going to take the limit as n goes to infinity. So that's going to be the exact mass, and that's going to be the limit as n goes to infinity. And you see that what we have here is exactly the same kind of definition of the definite integral. That's the integral from a to b of the density function, dx. So the interpretation in this context is that the integral gives us exact mass, not exact area. So that's the second interpretation. A third interpretation is probability. And so if you've taken a probability course, you've probably seen that probabilities for ranges of continuous random variables are given by integrals. So if you've got a continuous random variable x, the probability that a is less than or equal to x is less than or equal to b is the integral from a to b of f of x dx, where f of x is what's called the probability density function. Density, just like density in mass. So there is actually an analog there between probabilities and mass. The total probability is analogous to the total mass through exactly this kind of argument. So there's three different interpretations of a single integral, and we're going to use those interpretations throughout the course when we move into double integrals. In the next section, we're going to look at not a single Riemann sum, but double Riemann sums. See you then.